Hello everybody. Today I present you a synthetic near-field corner frequency analysis of two large-scale 3D dynamic rupture simulations of the 2019 Ridgecrest sequence and the 1992 Landers earthquake. This work is part of my master's thesis supervised by Alice-Agnes Gabriel and Taufiqurrahman. The analyzed data is generated in the two dynamic rupture simulations of the Ridgecrest sequence and the magnitude 7.3 Landers earthquake. The Ridgecrest sequence consists of the magnitude 6.4 Seals Valley foreshock and the magnitude 7.1 main event. The static stress change from the foreshock was used as an input for the main event. All events are dominantly strike slip events. The models incorporate complex 3D fault geometries, 3D velocity models, high-resolution topography, off-fault plasticity, and heterogeneous stress field models. Both models are capable of reproducing a broad range of observations. And there's a separate SSA presentation about the Ridgecrest model by Alice Gabriel for the session Exploring Rupture Dynamics and Seismic Wave Propagation along Complex Fault Systems. Apart from the on-fault rupture dynamics, these models produce synthetic near-field strong motion waveforms at over 1 million receivers respectively. And to exploit this high receiver density, we want to use the spectral corner frequency as an approximation for a waveform's relative frequency content in form of a single scalar quantity. So we are able to analyze its high-resolution spatial variability. And in the following, I want to show that there's great potential to infer rupture mechanics and near-field hazard variability from the near-field corner frequencies. At first, I want to give you a brief introduction to the corner frequency in general. On the left, you can see the theoretical amplitude displacement spectrum for the Haskell fault model of a line source. It's flat for the low frequencies and proportional to the inverse frequency squared for high frequencies. The frequencies that mark the kinks between the different slopes are the corner frequencies, which are controlled by the apparent rupture duration time and the rise time. The far-field spectra of real earthquakes look mostly quite similar to this theoretical spectrum, but often only one corner frequency can be identified. For our analysis, we work with the widely used Brune model, for which the displacement far-field body wave spectrum is given by this equation on the right. Omega 0 is the amplitude of the flat part of the spectrum and proportional to the seismic moment. Fc is then in this case single corner frequency and n the fall-off rate above the corner frequency, which is equal to 2 for the Brune model, the same as for the high frequencies of the Haskell fault model, and also in agreement with observations of real earthquakes over a wide range of magnitudes. Now I shortly explain how we pick the corner frequencies. We use the full near-field displacement spectra and do not try to separate them into P and S wave spectra, because we are not interested in inferring source dimensions, but want to analyze the variability of the relative near-field frequency content. As a first step, it's important to perform the integration from velocities to displacements in the frequency domain to avoid artifacts from transforming a non-periodic signal with static displacement. And then we calculate the misfit between the displacement spectrum and different theoretical Brune spectra with different corner frequencies within a realistic range. And then the Brune spectrum with the minimal misfit dictates the corner frequency. For this approach, the near-field waveform spectrum is interpolated to an equal frequency spacing, and we use the spectral seismological misfit, which is a logarithmic misfit criterion, in order to write high and low frequencies equal and to prevent an overwriting of strong oscillations. In this plot on the left, you can see an example of a synthetic displacement spectrum together with the corresponding Brune spectrum, and the picked corner frequency. At this point, it's important to state that our analyzed waveforms do not match all the theoretical assumptions of the Brune model, since we are not in the far field and surface path and side effects might be involved. But apart from the extreme near field, the observed spectra are in general rather similar to the Brune type spectrum. Now I present you our results for the Landers model. We calculated the corner frequency for more than 10,000 receivers in the near field and plotted them as a contour map. The horizontal components contain not much valuable information, just some minor radiation pattern and directivity effects. But as you can see in the plot in the middle, the vertical component of the strike slip event shows a strong variability with a striking pattern of waves with elevated corner frequencies, and those waves mostly have an angle close to 45 degrees to the rupture forward direction, and they trace the curvature of the segmented fault system. What's especially interesting is that the waves originate from areas with high accumulated slip and major surface rupture, as you can see by comparing them with the final slip distribution on the right. The waves partly correlate with the vertical peak ground velocities, as you can see by comparing with the plot at the right bottom. At 3 stations on or between the waves, there's real data available, so we did a comparison with our synthetic spectra. Overall, the observed spectra exhibit a good fit in the frequency range from 0.05 to 1 Hz. At Fort Irwin, which lays between two waves, the observed corner frequency is slightly lower than the synthetic one. At Barsdorf, it fits nearly perfectly, and for Jermo, the observed corner frequency is clearly higher than the synthetic one, but this station lays on a high frequency way, and therefore we infer that the observations agree with the observed high corner frequency waves of our simulation. In this plot, we can also see that the corner frequencies in rupture backwards directions are overall lower, which reflects the directivity of the unilateral strike slip rupture. But we can also observe sensitivity to non-source effects. For example, the high corner frequencies in the south represent the outline of the low velocity sediment basin of the Salton Sea. And also the high corner frequency in the west are based on side effects. We did an equal analysis for the Ridgecrest model, this time with frequencies up to 2 Hz. For the magnitude 7.1 main event, again, the vertical component has a complex pattern of increased corner frequency waves. This time there are waves in both directions of the fault, which agrees with a more bilateral rupture. There are again 2 waves that point at areas of high accumulated slip and major surface rupture, and what's most interesting, the gap between these waves coincides exactly with an area of less final slip and nearly no surface rupture. The orthogonal fault acted here as a barrier, and the rupture could break through the barrier only at depth, and then had to rupture upwards again. So taking a closer look at the velocity waveforms on and in between those waves reveals that the high corner frequencies are associated with single high frequent velocity pulses, which are not present within the gap. The magnitude 6.4 Seals Valley foreshock mainly ruptured along a fault which is orthogonal to the main fault of the magnitude 7.1 event, and the vertical corner frequency map also differs strongly from the main event. It has a large shadow zone in backward direction, which reflects the unidirectional rupture. There's only a small area with higher corner frequencies in backward direction that might stem from the small part of the rupture along the orthogonal intersecting fault. Then there are again high corner frequency structures that point to the area of maximum accumulated slip and major surface rupture, but this time they have sometimes angles of nearly 90 degrees to the rupture. Then, an especially striking feature is a curved ray that can't be the product of a source mechanism. Further analysis of the Wavefield showed that this ray highlights a deflection at a strong velocity contrast under a mountain range. This major geologic path effect can be seen also in the horizontal components and is therefore very relevant for seismic hazard assessment, but can't be captured with GMPEs. After finding this feature in the corner frequency plot, we also noticed it in a video of the wavefield propagation. So now here you can clearly see how the wavefield is deflected at this mountain range, and energy is propagating in a completely unexpected direction, and our corner frequency analysis makes this effect perfectly visible. After seeing the results, there's now the question, what are we exactly observing? We saw that the corner frequency is influenced by directivity, geologic path, and side effects. Apart from that, we think that the mechanism that is responsible for the rays pointing to the areas of high accumulated slip and surface rupture is based on high-frequency radiation caused by the rupture breaking the surface, which is also associated with strong decelerations of the rupture. But we are looking here at very complex models, and we have a superposition of different effects. We have seen, for example, that some high corner frequency rays correlate well with PGVs, while others clearly don't. We plan for the future to do this kind of analysis for simpler models, where we can control the different model parameters to gain a more quantitative insight. We showed that near-field corner frequencies of the vertical component of strike-slip events contain information about rupture directivity, surface rupture, on-fault slip distribution, fault segmentation, and path effects. This analysis approach could help to identify hazard-relevant features in large datasets that can't be predicted with GMPEs, as for example, major geologic path effects. In addition, the rise of distributed acoustic sensing and high-rate GNSS networks highlight the potential of dense ground motion observations in the near field of large earthquakes. Our approach then could be used for inferring earthquake kinematics and understanding earthquake physics directly from near-field data. Until then, synthetic studies are crucial to identify what to look for in the vast amount of data generated. Thank you for your attention, and now I'm looking forward to your questions.